I had a question, Professor. I'm
Hmm.
still confused with number six.
Number
Um,
6. Okay.
more, more specifically, well, in general, number six, I'm confused, but I picked E because it looked like the toughest one. Do you mind if we do that one as an
Yeah,
example?
no problem. No problem at all. So when I say resonance form, what does that mean to you?
What I wrote down was um, a different way to write. Um,
Yeah, so and basically these are Lewis structures,
yeah,
right? And so it's in a lot of instances, particularly with organic um, molecules, with double bonds and that sort of thing. There's a lot of different ways to do it. So that's basically all that is. So you want to do pyridine, the,
uh,
the fourth one or the fifth one?
letter E. Oh, the fifth one?
Oh, the allylion. Allol. That one?
Yes.
Sure. Okay, let us do it. So let me get, so let's draw it out so we can make it bigger. C, H, H, and the whole thing has a negative charge. So it's a rare thing. It's a hydrocarbon that's also an ion. You generally don't see that very often.
Sorry, Professor. And then one more hydrogen in above the carbon in the middle.
Oh, you're right. You're absolutely right. That would make for a much more interesting molecule. Um, okay, so how do we start? Whenever you're doing a Lewis diagram, how do you start?
Count how many electrons we're supposed to have.
Exactly. So we've got 3 carbons and 1, 2, 3, 4, 5 hydrogens. So that's how many valence electrons for carbon?
12 in total. Oh,
Yeah,
well, four.
3
Four.
times 4, 12. Right. You jumped ahead. You're much more clever than I. And 5 hydrogens. Hydrogen is just 1. So 5 times 1 is 5. That's 17 electrons. Right?
And then we have that extra negative charge.
Right. Exactly. Plus 1. Always should give you pause when you see an odd number of electrons, because that means that somebody's going to get 1. And when that happens, generally you have that's a highly reactive, unstable molecule. So you want to see that it has an even number. Either 1 gets taken away, or 1 gets added, or 3 get taken away, or 3 get added, something like that. But generally, there's going to be an even number of electrons. Not always the case, but generally that's the case. So we have 18 electrons. So how many electrons do we have in bonds here?
14.
2, 3, 4, 5, 6, 7. Yeah, 14. Right. So the question becomes, we have 4 electrons left. So now you start to look for who needs electrons. So do any of the hydrogens need electrons?
No.
No, because they just have 2, and each of them has a bond, so they're all fine. What about the carbons, though?
They do. Yeah, I would put the last two. We have 4 electrons left. I was thinking put a double bond between um, the middle carbon to its
Well,
left.
let's distribute the electrons first before we start
Okay.
talking about double bonds. So where should we put them? I guess it doesn't really matter where we put them. You can put them, as long as we don't put them all in the same atom. So we could put 2 there and put 2 there. That's probably the most reasonable way to do it.
Okay.
Okay, so now what do we do? So the one in the middle still doesn't have enough. And the other 2 seem to, let's see, they have 2, 4, 6. They have 8. So each of those on the outside. So we have carbon 1, carbon 2, carbon 3. So carbons 1 and 3, how many electrons do they have?
They have 8.
Yeah, so they're fine as far as octet goes. They're okay. What about valence electrons?
5.
Yeah, these have 5. So there'd be a negative charge here and a negative charge here. What about the carbon in the middle?
Only 3.
That is only 3. There'd be a positive charge. So that's, I mean, that is a potential way of doing it, right? Because that, the only problem is the carbon in the middle does not have an octet. So that's an issue. We need to deal with that. So how are we going to deal with that?
You could move the pair from carbon 3 to double bond with carbon 2.
Mm-hmm. That works. And then...
And I think you would have to do the same for carbon 1 to carbon 2 to give the correct amount of valence.
And can we do that, though? Is that possible? So if we do that, let's see what, I'll show you there's an issue with that. Okay. So let's do that. So we move this.
Oh, the total amount.
Do you see the problem?
Yeah. Okay.
So what's the problem with that?
It passes the octet rule for the carbon 2.
So carbon 2 now has 10 electrons, and can it do that?
No.
No. We could get away with that if instead of carbon that was silicon. If that was silicon, we could do that. But we can't do that because it's carbon. It's only in period 2, so it cannot do that little trick. So we're going to have to take that bond, take that bond away and give those 2 electrons back to carbon 1. So now let's see where the charge is now. So who has a net charge? Which atom has a net charge at this point?
Carbon 2 has a positive charge.
Does it? How many valence electrons does carbon 2 have?
4.
Mm-hmm. And how many should it have?
5.
Carbon should have 5 valence electrons?
Oh, sorry. Sorry. 4, yeah.
4, right. So carbon 2 is okay. What about carbon 3?
That one's correct too.
That one's fine as well. So remember, the more you do these, the more practice you have with these, the more the patterns start to emerge. Carbon generally 4 bonds and no lone pairs. So if you see carbon with 4 bonds and no lone pairs, it's fine. That's generally the situation carbon finds itself in. So carbon 2 doesn't have a charge, carbon 3 doesn't have a charge, and yet there's a negative charge somewhere. Where is it?
Carbon 1.
Carbon 1. Right. So why does carbon charge? Why does carbon 1 have a formal charge?
Because it's supposed to have. It's in group 4, but it has 5 valence electrons.
Right. It has 1, 2, 3, 4, 5. So that carbon is negatively charged. So that is one way of drawing the allyl line. What's the other way?
Instead of making carbon 3 look like carbon 1 and carbon 1 looking like carbon 3.
Right. So the other way of doing it would just be H and then. So that's the other way of drawing it. So those are 2 resonance forms. Now, do you remember what the hybrid form would be?
Is that the one where we draw the dotted line to go back and forth?
Exactly. So how would we draw that? Let's just take this first one. How would we make that so that it was sort of the same all the way across?
So I'm not sure, but I would put the lone pair right there on carbon 1, and then draw a dotted line to carbon 3 and add a lone pair there.
So, but then carbon 3 would have more than 8 electrons.
And remove a bond from carbon 3, carbon 2, and remove the lone pair.
Yeah, basically we would take this bond away, put the lone pair there. And so what we would have is this pair of electrons being shared among all 3, and this pair of electrons being shared among all 3. And so that's basically how you would draw the hybrid structure. And so you have basically 4 electrons being shared by 3 carbon atoms. And so they would all have basically a partial negative charge.
For the second dotted line, I'm not too sure, what does that one represent that you drew?
Well, one dotted line is a pair of this bottom line. Man, I'm having a hard time today. This dotted line below is a lone pair of electrons, and that dotted line above is a lone pair of electrons, and they're delocalized around all 3. So basically, so you would sort of have like the same way we'd have P.
Yeah.
Being both above and below. Basically, we'd have a pair of electrons. We'd have a density, like a cloud of density of 2 electrons above, and we have a density of 2 electrons below. Where a pi bond is basically having 1 electron above and 1 electron below the density. This would be twice as much. So basically, it's almost like you'd have a double bond above and a double bond below.
Excuse me.
Mm-hmm.
Can we draw like this? The dotted line here. Like that. Sorry. 3 carbons? Sorry.
So, let's see, let's do it again. So, have a double
Can we draw
here,
like,
a double there.
no, put 2 dotted lines between the 3 carbons.
Yeah, that's what I drew basically. But remember that. But there's. So I'm sorry. So have a double bond there. Oh, not there. Duh. What am I doing? Can't have a double bond with a hydrogen. No, there's 2 pairs there's 2 lone pairs of electrons.
I mean, like do like this.
It's too many electrons on this carbon. That gives that carbon too many because it already has an octet, so we can't give it any more.
I mean, never mind.
Yeah, so you have to just imagine single bonds all the way around, and then a lone pair, 2 lone pairs being shared between 3 carbon atoms. All right, shall we do the one above it as well? While we're here.
And, also, before we do that, so do you want us to show? Sorry, what was the last part?
Oh no, just do the resonance forms. But
Okay.
there is a question in there about hybrid forms. So I just want to introduce
Okay, thank you.
the idea of there's a hybrid form that's basically the average of the 2 resonance forms, or there's 3 or there's 4 resonance forms, and it's the average of all of them. So here we have pyridine. Pyridine is a particularly nasty chemical that you do not want to mess with. So how would we draw that one? So we've got carbon, carbon, nitrogen, carbon. 1, 2, 3, 4, 5, 6. H. Okay, so how do we start?
There are 5 hydrogens. That is 5.
So hydrogens,
And
nitrogen, carbon.
nitrogen, 1 nitrogen. That is 5. 1, 2, 3, 4, 5 carbons. That is 5 times 4. That's 20.
So 30 electrons total. And how many do we have in bonds?
1, 2, 3, 6, 7, 10, 20.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where's it 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. 11 bonds.
Yeah, 11 and 22.
So that's minus 22, so we're left with 8. Okay, so we have 8 electrons left. So who needs electrons?
Nitrogen.
Yes, nitrogen. What does nitrogen normally look like? When you see nitrogen in a molecule, what does it normally look like? How many bonds and lone pairs does it normally have?
3 bonds, 1 pair.
Yeah, it normally looks like that, right? Because if we do the dot structure for just nitrogen, we go 1, 2, 3, 4, 5. So that tells us we're going to have a lone pair and 1, 2, 3 bonds. So we just go ahead and probably do that for nitrogen. So give it the lone pair and give it another bond with one of the carbons. Doesn't really matter which one. Let's say that one. So that now we're down to 4. So where else are we going to put another electron, another pair?
Carbon on the left bottom to
Oh, I'll just put numbers on them. So 1, 2, 3, 4, 5. There we go.
carbon 2, carbon 3.
So carbon 2 has how many valence electrons? It only has 3, and it only has 6 total, so it could use another pair. Now we're down 2. So we have 2 more left.
2 more left. Go to carbon 4.
Okay, put them on carbon 4. So now we're done. So that's all our electrons. So now we look and see who still doesn't have sufficient number of electrons. So do all the carbons have an octet?
No.
So which ones don't?
3, 5.
So 3 has only 6 total electrons. It has 3 bonds and no lone pairs. So it's missing a couple of electrons. And yeah, 5 is in the same position. 5 only has 6 total electrons from its 3 bonds. So they're electron deficient, and we need to do something about it. So what do we do?
Move the lone pairs to on carbon 2 to make a bond with carbon 3.
So move these to 3 to make a double bond. Okay. And then what about carbon 5?
Those 4 on to 5.
those go here and make a double bond. So then we get rid of the lone pair. Now we look and see, does everybody have an octet that needs an octet? The hydrogens obviously are fine. Do all the carbons have a sufficient number of electrons now? Oh, Ariana, were you answering the question just now? I can't tell when the, yes, excellent. So there's no timestamp on the chat, so it's kind of hard. Did you type that an hour ago or just 3 seconds ago? Yes, every carbon now has a sufficient number of electrons. So this is a valid structure. Nitrogen has an octet. It has its 3 bonds and a lone pair. So it has 8, and each carbon has 4 bonds. So for a total of 8. So everybody's happy. But what's another way you could draw this structure?
Can you clear it for now to draw another way? I mean, clear some bounds.
Where is my erase? Oh, there it is. There.
Can I draw this way?
I don't know what that is, but
Nitrogen carbon 3 bond.
no. No, look at the structure. The structure over here. There's no bond between. That's not what pyridine looks like.
Okay.
Yeah.
Oh, okay. So, where's clear? Where's my clear stuff? Yeah. Oh, yeah. Okay. So this way, and this way, and this way.
Right. You basically just move the double bond to the other side. And when you take organic, you see basically the way we represent that is to just make an arrow that does this, showing you that that double bond can basically move. It moves around. And so this is what we call an aromatic ring, because basically none of these actually have a double bond. What do you think the bond order of these bonds are? Every one of these bonds in the middle, what do you think the bond order of those are?
$1.5.
Yeah, exactly. None of them are single bonds, and none of them are double bonds. They're in between. And so the way we represent, so in organic chemistry, the way you represent a ring like that is you draw it like this. You go 1, 2, 3, 4, 5, 6, and you put a circle in the middle, showing you basically that all of those bonds are equivalent. So right there, that's benzene. And then for pyridine, we just put an N here, showing the difference. So this represents the fact that all of those bonds are the same. Basically, they're not doubles, they're not singles, they're intermediate. So this would be the hybrid structure. And the two resonance structures are just double bonds on one side, and the other one is double bonds on the other side. So any questions about that one?
Yeah, Professor, so
Yeah.
do you want to draw one structure and just the arrows, or draw 2 different structures?
Well, and the question says right resonance form. So you draw 2.
Okay.
Yeah, or however many it took. Because for instance, carbonate might be more than, I think there might be more than 2 for that one. And phosphate, we definitely know there's more than 2 for the phosphate ion. There's more than one way of drawing that one.
Okay, thank you.
Okay, any other And I guess we're done. So do you want to try a different question or stay here? What people like to do?
I wouldn't mind going over number 9 or
Sure.
any of number 9. I think you were just
we can
talking
do that.
about hybridization and delocalized.
Oh, there you go, hybridization. So here we're talking about the hybridization, SP, SP2, SP3, and whether or not, now this is the other form of hybridization, whether or not you'll see a hybrid structure, whether there'll be more than one structure you can draw from that, and whether the electrons will be delocalized, whether they'll be stuck in a double bond on one side and a single bond on the other, or will they be delocalized and go between a central atom. So yeah, you want to just start with ozone?
Okay.
Yeah, ozone's a fun one to do. So let's just go 1, 2, 3. And how many, and there's no charge, right? Ozone is a neutral molecule, it's not an ion. So how many total electrons do we need for ozone?
18.
18, yeah. Each of them has 6. 3 times 6 is 18 electrons. And we've got 4 electrons in bonds. So we have 14 left to give out. So where are we going to put them?
I'll just go from left to right. So
oh yeah, I should just name them. So oxygen 1, oxygen 2, oxygen 3. It'll make things easier.
So for oxygen 1, I'll give 6 electrons. Oxygen
yeah,
2.
That's probably not a bad way to start, because remember when we draw these things, the way we normally go is if we hit at the start, we have a whole boatload of electrons, and basically we decorate the outside of the molecule. And we give everybody on the outside a full octet. And then if there's any electrons left over, those go in the middle. So that's definitely a good way to start. So go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I have 2 left, so those go in the middle. Okay. So now it's time to look at my octets. So we know that oxygen 1 and oxygen 3 have octets because we gave them octets. So that's not an issue. But what about oxygen 2?
It does not.
We're not boring you, are we, Raymond?
No.
Okay. Yeah, it doesn't. So how many does it have?
6.
It has a total of 6, right? 2 bonds and a lone pair. So how are we going to address that?
We could bring a lone pair or a pair of electrons from 3 to 2 to make a double bond.
Yep. So put a double bond there and take away that lone pair. So how many total electrons does O2 have now?
8.
So it's got 8. So everybody is an octet now, right? But but interestingly, they all have them in different ways. So oxygen 1 has 6 lone electrons and 2 in a bond for a total of 8. Oxygen 2 has 2 by itself and 6 bonds for a total of 8. And oxygen 3 has 4 lone electrons and 2 bonds for a total of 8. So they all have different ways of getting there, and which should tell you something about their charges. So now, first thing, get everybody an octet. Good. Second thing, now we have to see what the formal charges are. So what's my formal charge on oxygen 1?
There's no charge.
So how do you calculate it?
So it's supposed to be 6 valence
Right.
electrons.
Supposed to have 6. Whoops.
Oh, actually, so
So
it
instead of
has
6, and then we subtract the number of valence electrons it actually has in this structure. So how many
Actually,
does it have here?
7.
It has 7, right. So it has 3 lone pairs for 6, and we count one of these from the bond. So that's 7. So it actually has a negative charge. Now what about oxygen 2?
It has
It should have,
supposed to have 6.
supposed to have 6. How many does it have?
It does have 6. Wait, sorry. 1, 2, 3, 4. It has 5.
It has 5, right, because it has these 2, 3, 4, 5. So it only has 5. So it actually has a positive charge. And then what about oxygen 3? It's supposed to have 6 valence electrons, and it has
6.
6. So there's no charge on that one. And like I said before, that's one of the patterns you will see. Oxygen, if we count the number of valence electrons, 1, 2, 3, 4, 5, 6, it's going to have 2 lone pairs and make 2 bonds. And that's most of the time, that's exactly what it does. And when it does that, it doesn't have a net charge. So we have 2 things. We have 2 oxygens with charges. But when we add them together, what do we get?
0.
We get 0. So this works, right? This works as a structure for ozone. It has charges in it, but it has a net charge of 0. So there's 2 questions here. The first question is, what is the hybridization of oxygen 2? It's the central oxygen. So how do we figure out what its hybridization is?
So there's 3 regions of electron.
Exactly. 1, 2, 3. And if you have 3 regions of electron density, what hybridization is that?
sp2.
Yes. It's sp2. So what shape would this be?
Sorry, I don't have the paper open.
It'd be planar.
Trigonal planar.
Yep. Yep. So it would look bent because we don't include the so the overall structure, the overall geometry of it is trigonal planar, but it would appear bent because we don't include the lone pair when we talk about the shape. So it would actually look just like this. It would look bent. So that answers that question. So we know the hybridization is sp2. What about the other? Would the electrons be delocalized? What does that mean?
I'm not too sure what that means.
Okay, anyone want to help him?
And resonance.
Right. Is there a possible resonance structure here?
Yes.
Yes. So what's another way we could draw this?
Spin it. Make oxygen 1 become oxygen 3, and oxygen 3 become oxygen 1.
Right, we could just move this double bond over here. So that now oxygen, wait a minute. Yeah, sorry, that doesn't go like that. Do that again. But what happened is basically the electrons would then just move in the other direction. So this lone pair would become a double bond. And then this bond would then become a lone pair. So basically that pair of electrons jumps from oxygen 1 to oxygen 2 back to oxygen 3. And so now this is positive, or wait a minute, this is no charge. This stays positive, and now this one's negative. And then basically back and forth, back and forth, back and forth. So would the electrons be delocalized?
Yes.
Yeah, if you can form a resonance structure, that means the electrons are delocalized. It means sometimes they're in this position, sometimes they're in this position. Sometimes they're on Sometimes the double bond is on this side of the oxygen number 2, and sometimes it's on this side. But we know what actually is the case. What would be the actual case here? What would that really look like? How would we draw that? The hybrid structure. Remember, I can have a double bond on one side and a single on the other, or I could have a single bond on one side and a double bond on the other. Right. We would just have that extra pair of electrons would be shared, be delocalized around all 3. And so we would have a bond order of 1.5 here and 1.5 there. And that's what we see, because when we look at ozone, when scientists look at ozone, you shine like a laser light on it, and you see basically how the bonds are vibrating. That gives you an idea of like how the bonds are vibrating. That shows how the bonds vibrate dictates what light they absorb. And so if we had a double bond on one side and a single bond on the other, it would absorb 2 different wavelengths of light, one for the double bond and one for the single, but it doesn't. It absorbs 1 wavelength of light.
Excuse me.
So it shows that both of these are the same. Yes.
What's the shape of the oxygen 2 now?
The same. Because it still has 3 regions of electron density. It has the lone pair. It has a bond and a half on this side and a bond and a half on that side. So there's still three regions in space where there are electrons. Yeah, so it's still sp2. No, excuse me. All right, so is there? Why don't we do CO2? We see if there's a difference there. Let's do CO2. So we've got carbon here, oxygen, oxygen. So what are my total number of electrons for carbon dioxide? Total number of electrons for CO2. 1 carbon and 2 oxygens.
The carbon is in group 4.
Yep, so carbon's got 4. What about oxygen?
It's going to be 2 times 6.
Yep. Oxygen's a group 6. So we have 4 and 12. So we get 16 to go. 16 electrons. We have 4 in bonds because we have 2 bonds. That leaves us with 12. So what do we do with our 12 electrons?
Start with the outside. You could give each oxygen.
Yep. Yeah, basically give each oxygen 6. Give each oxygen a full octet. So they have 2, 4, 6, 8, 10, 12, and I'm done. So that's all the electrons I have. So oxygen 1 has a full octet. Oxygen 2 is a full octet. What about the carbon?
No.
Carbon is not happy.
Carbon's very unhappy. Because how many total electrons does carbon have now?
4.
Total. It's only got 4. It's got 2 bonds, 2 electrons each. So it's only got 4. So it is far from an octet. So how do we deal? How do we cope? What do we do?
Take 1 pair from oxygen 1 and another pair from oxygen 2.
And make double bonds. Yeah. So that gets rid of that lone pair. This gets rid of that lone pair. So the oxygens still have an octet because now instead of having 6 electrons in a bond, they have 4 electrons in 2 bonds for total. So they have 4 electrons in lone pairs and they have 4 electrons in bonds. So they're still both happy. What about the carbon now? Does the carbon have a full octet?
Yes.
It does, right? Because it's making 4 bonds like carbon generally does. And there's 2 electrons in each bond, so that's 8. So carbon's happy. So nobody has a charge and everybody has an octet. So stable structure. So 2 questions. One, what is the hybridization of the central carbon?
SP.
Why do you say that?
There's 2 regions of electron density.
Right. We have a double bond over here. That's 1. We have a double bond over there. That's 2. SP. So will the electrons be delocalized around the central carbon?
I would say no, because I think there's only that way to write the structure.
Exactly. Yeah. We can't draw it any other way. We can't put we could draw it all kinds of crazy ways, but then that would introduce charges and violations of the octet rule. We can all kinds of things. This is the most stable form. In fact, CO2 is extremely stable. I mean, that's why, you use it to put out fires and all sorts of other things. It's really, really stable. Because, carbon's double bonded on both sides, and that's the end of that. And everybody has the requisite number of electrons. So no delocalization here. One other question. Which electrons of the carbon make the sigma bonds? So I've got 2 sigma bonds and I've got 2 pi bonds. Which of carbon's electrons makes the sigma bonds? Where would I find them? What orbital would I find them?
In the s orbitals?
Nope. Remember, there's no s orbital anymore. Why isn't there an s orbital anymore?
Oh, because we're just looking at the valence electrons.
Mm-hmm. And what happened to the s orbital?
It's now SP.
Right. It's been hybridized. It no longer exists. So we've taken one of the p orbitals and the s orbital, and we've mixed them together to make an sp orbital. So whose electrons are making the sigma bonds? So remember, when this hybridizes, carbon's got 4 valence electrons. So now it has 2 sp orbitals with an electron in each one, and it has 2 p orbitals left over with an electron in each one. So who makes the sigma bonds and who makes the pi bonds?
The sigma bonds are in the sp orbital, and the pi
Right.
bonds are in the p orbital.
Exactly. Yeah, remember, sigma bonds are always made with the hybridized orbital. That's the whole point of hybridizing these orbitals, is to get them so that there's electron density directly between the atoms. That's the whole point of making them, is to sort of force you to get that electron density in between the 2 carbons directly. And then the p electrons are used to make p makes pi, right? P makes pi. So electrons make a pi orbital, a pi bond over on that side, and another one on the other side. Yeah, right. That's how you do that. Good job. All right, who is next? Oh man, it's ever windy out. Yikes. So who else has a question? No point being shy at this point. I mean, you guys got a test next week.
I have another question.
Right. I love it. What is it?
We could go over percent composition for number
Sure.
11.
Sure. Blast from the past. Actually, we're reintroducing it in chapter 6. So percent composition, that is down here. Okay. So, yeah, just pick one. We'll go through it.
I guess the first one, because if I seen that on the test, I think I would be thrown off.
Okay. Yeah, don't be thrown by the name. That's just a name. So, yeah, I mean, photographic fixer. You guys are way too young to remember what photographs are. So it doesn't come out of an inkjet printer. Because I'm, at the advanced age I am, I remember developing X-ray film when I was a graduate student. That's how we used to. You'd use radioactive tracers in DNA and RNA to see how much DNA was being replicated or how much RNA was being made, that sort of thing. And you'd run it out on a gel to separate the different sizes, and you put a piece of X-ray film next to it and leave it overnight. And then the radioactivity would hit the X-ray film, and then you would develop it in a dark room. You'd first put it in silver, actually, solution of silver, and then you would fix everything in place with this solution, sodium hyposulfate, I believe, hyposulfate, and that would fix everything in place. So, and it's kind of smelled nasty, if I'm to be honest. So, what does percent composition mean? Like when we say percent composition, what does that actually mean? What am I looking for here? I mean, if we can't define percent composition, we're going to have a hard time answering the question, presumably.
What a certain element, how much of a certain element makes up a molecule?
Mm-hmm. With how are we measuring the elements? That's the critical thing.
By moles?
No. See, that's the difference. It's by mass. So basically, if we had 1,000 grams of this, I would buy it from Kodak or wherever, and I'd buy it. Actually, you'd buy it by the liter, or I think you might buy it by the kilogram. So I had 1,000 grams of this stuff. Out of that, how many grams would be sodium? How many grams would be sulfur? And how many would be oxygen? That's what we need to know. That's what percent composition means, is percent mass. So that's what we need to determine here. So what would be the very first thing to do?
Do we find
the molar mass of this compound?
Yeah. So basically we're asking ourselves, if I had a mole of this stuff, how much would it weigh? What would be the mass of it? And then from there, you're right in one sense that we're going to have to deal with moles. You can never get away from moles. But the moles will tell us what the mass of each atom is in a mole of the molecule. So we determine the mass of a mole. And then from that mole, how much of it is sodium, how much of it is sulfur, how much of it is oxygen. And then give a percentage of each one. So what's the mass of our photographic fixer here?
158.11 grams per mole.
So you just look that up?
Yeah.
There you go. That's the quickest way to do it. So 158.11 grams per mole. And remember, we want 4 significant figures. So you'd have to find at least, when you looked up the mass of it, you'd have to find at least a mass with 4 significant, if not more. And generally you want more, because you always want to round down later. So have more accuracy than you need, or more precision than you need to start. So that's the mass of 1 mole. So out of that mole, how much of that mass is sodium? How would we figure that out? First question is, if I have a mole of fixer, how many moles of sodium do I have in that mole of the compound?
Am I just taking the mass of sodium?
Well, right now I'm asking you, if I have a mole of this compound, how many moles of sodium do I have?
1 mole.
2 moles.
2, right? Look, you have to look at the.
Oh, okay.
At the. It tells you right there what's in the formula. How many? That's the whole point of the formula, right? Is to tell you, if I have 1 mole of this is how many moles of each one. If I have a molecule of this, how many atoms of each one? And basically it's the same thing. So I have 2 moles of sodium. So that's 2 times, now, what's the mass of 1 mole? There, you would just look it up in your periodic table. Hopefully you have your periodic table in front of you.
It's going to be 22.989770.
That's probably enough. 22.9897 or 8, I guess, 77.
Yeah.
All right. So there you go. And what about sulfur? How many moles of sulfur would I have?
2 as well.
2, right. How much does 1 mole of sulfur? What's the mass of 1 mole of sulfur?
32.065.
Okay. And oxygen, how many moles of oxygen?
3.
Mm-hmm. Nope. I remember this one. Okay. So then we just figure out what the total mass of each atom is in a mole of this molecule. And it also helps us double check and see if this is correct. Because we could have looked up, it's really easy to look up the wrong one. You leave out you put in Na2SO3, and then you get something different. So what are my 3 masses? What's my mass of sodium?
45.9796 grams.
So 45 point what?
9796.
9796, okay. And what's my mass of sulfur?
64.13 grams.
64.13. And my mass of oxygen?
47.997 grams.
7. So when we add those together, hopefully we get 158.11. Do we?
158.1066.
Yeah. So we get the same amount. So we're good. So how do we figure out? So that tells you that we've done this correctly. If we add those 3 up and we get the molar mass, we're good to go. Now, how do we figure out what the percent composition is?
For each one, I'll just start with sodium. Will we
Mm-hmm.
just divide the grams of sodium by the total grams of the molecule?
Yep. Yeah, so that would be 45.9796 grams divided by 158.11 grams. That we cancel out grams, and that gives us a fraction, which is what we're looking for. Percent just means a fraction, right? So what do we do with this fraction to give us percent?
Times it by 100.
Right, right. So instead of fractional composition, we get percent composition. So what would be our percent composition of sodium?
29 point, how many significant? Oh,
We want 4.
29.08%.
Yeah, and then you do the same thing for sulfur, you do the same thing for oxygen. And then you make sure that when you sum them, you get 100%. If you don't get 100%, then something's wrong. Okay, so you should, when you finish it, it should sum to 100. If it sums to 90 or it sums to 110%, then something's squiggy there. So everyone clear on how that works? And remember, we can do this in reverse, like on the next question. Basically, we flip that on its head and we do it in reverse. And we're given what's the percent, we're given the percent composition. And then we have to figure out, well, with those percent compositions, what is the molecular formula? So it's basically doing the same thing, but in the opposite order. So is everyone clear on that one? C?
Yes.
Okay, cool. All right, who's not going to make Nick ask all the questions today, are you? Some other brave soul. You're the only brave soul here today, Nick, asking questions. So, you know, everyone else wants to ask them, but
It might be because I'm the only one that hasn't studied that much.
I don't think so. All right, who else has a question? Ahmed, how you doing today, man? You must are you good in everything here? Is there a head scratcher in there that you've seen? Ahmed, you still with us?
Yeah, Professor. I'm still with.
So
you
you have any questions?
I'm doing fine, thank you.
Okay, you're just hanging out?
Yeah, I'm seeing what's going on, and I'm gonna try to take another look at the video, and I'll figure out then. Thank you.
Okay, no worries. All right, so anyone else with a question? Or want a little reminder of how to do some of these? Because some of these we haven't done for quite a while. Like, yeah, I'm glad you asked about percent composition, because it's been a long time since we looked at that. Does everyone just want to do it and then come back on Thursday and go over the ones they can't do? Does that seem like can we do number 10A? Excellent, Ariana. Yes, we can. We can do that. What is 10A? 10A, 10A, 10A. Oh, there you go. Yeah, I figured if somebody would want to ask this question. So when we first sort of were introduced to the idea of molecular orbitals, we were shown that some, as you went across the periodic table, certain elements would form strong bonds and certain ones wouldn't, just depending on how many electrons got put into bonding orbitals and non-bonding orbitals. And so what this question asks, can we have a boron-boron Can we make that? Can we make a boron-boron molecule? What would be the bond order of that? What bond order, if we can't get them to bond at all, what would our bond order be? If we run through all this, we figure out how many valence electrons and everything else, and then we figure out where to put them in bonding orbitals and anti-bonding orbitals. When we've done all that, if we figure out they can't bond at all, it's because their bond order is what?
0.
0, right. And what does that mean? From this, how do we figure out whether or not, how do we determine bond order using this formula? What is the formula for determining bond order?
Is it sigma minus pi bond divided by 2? Is that the formula?
You're close. You're real close. It is divided by 2, but it's not sigma plus pi divided by 2.
No, sigma minus pi.
Nope. You're real close, though.
Is it the electrons that bond minus the anti-bonding ones?
Bingo. There you go. Yeah, it's both sigma and pi. So remember, it's sigma plus pi. And then from that, you subtract sigma star and pi star. So these are the bonding electrons. Those are the good electrons. And these are the naughty electrons. These are the anti-bonding electrons. So the bonding electrons have electron density between the two atoms, and the anti-bonding orbitals have electron density away from the two atoms. So they don't bond. In fact, they do the opposite. So what we do is we take all the bonding electrons and all the anti-bonding electrons and subtract them and then divide by 2. You're absolutely right about that. We take some set of electrons, we subtract it from another set of electrons, and then we divide by 2. But the ones we want to do that with are the bonding and the anti-bonding. So let's do the first one. So boron. So basically what we have set up here is we have our atomic orbitals from atom 1 on the left side, and we have our bonding orbitals from atom 2 on the right side. And we figure out where they are in the atomic orbitals. Remember, those are S, P, D, and F, the ones we've come to know and love over the many, many months we've shared. And then we figure out where they go in terms of the bonding and anti-bonding molecular orbitals. So we'll put boron on one side. So here, we'll put boron on that side, and we'll put boron plus on that side. So how many valence electrons does boron have?
3.
3, exactly. So this boron has 3. And how many would boron plus have? A boron ion.
2.
Would have 2, exactly, because we've taken one away because now it has a net positive charge. So it only has 2. So where would we put so we have a total of 5. Sorry, again, having a problem with the old talking. Where would we put the valence electrons for boron between S and P? Where did we put them?
Two go into an S.
Mm-hmm. Yep. And the other one would go into P. There's pretty much no other place it could go. Now, what about boron ion? It only has the 2 electrons. So where do we put them?
In the S.
Yeah, 1, 2. All right, so now that's all the electrons I have. Don't have any more than that. So let's start filling up our molecular orbitals. So where do we start when we start with our molecular orbitals?
S sigma.
Mm-hmm. Now I just took the numbers off, so don't be freaked out. Oh my God, it should be a 2 or it should be a 3. I just took them off because then we could put whatever atoms we want here. So this is basically going to be our model from here on in, and you can put, you may have period 3 atoms or period 4 atoms, and then you would just change it from 2s and 2p to 3s, 3p, 4s, 4p. It really doesn't make any difference. It's just where are the valence electrons. They're either in shell 2, shell 3, or shell 4, shell 5, but the pattern will be the same. So we put the first 2, you're absolutely right, into bonding orbitals, and that's always going to be the case. The bonding orbitals are always going to be more stable, which makes sense. Bonding electrons, getting atoms to bond together is more stable than getting them to fly apart. So they go here. Oops, let me move this out of the way. Okay, so we got 1, 2. So that's, that's 2 gone. I have 3 left. Where did the next 2 go?
You put the next 2 on S, the anti-bonding one.
Yeah, S star or sigma star. Now I have 1 left.
And then the last one goes on P pi.
Mm-hmm. Okay, now I'm done. I don't have any more electrons left. Now it's a matter of figuring out what our bond order is. So let's do that. What would be our bond order here? So we figure out how many electrons do we have in bonding orbitals?
3.
3, that's absolutely right. 1, 2, 3. So we have 3. And how many do we have in anti-bonding orbitals?
2.
2. Those 2. Those naughty electrons. So yeah, so that's the total, that's our net number of bonding electrons. How do we determine the bond order?
You divide by 2.
Right. Because remember, every bond is a pair of electrons. A sigma bond is a pair of electrons. Pi bonds, a pair of electrons. They're both a pair of electrons. I mean, they're situated in different places and shared in different ways, but they're still 2. So if I have 6 more bonding electrons than I have anti-bonding electrons, that's 3 bonds. So in the same way here, I have 1 more bonding electron than anti-bonding electron. I divide my 2, and my bond order, therefore, is 1/2. So what does that mean? If I have a bonding order of 1/2, does that mean that it's theoretically possible? I mean, if I have a bonding order of 0, that means no, I do not form a bond. That does not happen. What about 1/2 though? Is that still possible?
Yes?
Yeah. There you go. Say it with confidence. Yes, but it's not very stable. Because basically what that means is I have 2 atoms sharing a single electron. So that's not super duper stable. It's possible that can form, but it's not very stable. Now let's switch this. So that was this molecule. Now let's look at this one. So the only difference would be instead of B plus, instead of having a B boron ion, I have boron itself. So this stays the same. So boron on the left stays the same, and I will replace this with boron as well. So they'll look exactly the same. They'll each have a pair in S and one in P. Now let's go through it again. And now I have, how many total electrons do I have this time?
Six.
Now I have 6. Last time I had 5. Now I got 6. So let's put our 6 electrons in. So let's start doing that. So how many do we have in? So we'll start the same way, right? And we have 6 electrons to include. So I'll start with where? Where do I start? I'm putting in my molecular orbitals now. I'm filling those in with my 6 electrons. So where do I start?
In S sigma.
Mm-hmm. 1, 2. And then?
And then another 2 on the anti-bonding.
Yep, sigma star. 1, 2. So I have 2 left.
And then you put 1 on P pi on the left, and then you put another on the right.
That's right. Excellent. Right. They go because, remember, we use the very same rules that we do for the atomic orbitals. These are called degenerates, right? Because they have exactly the same energy, just like the 3p orbitals have exactly the same energy. So when I'm filling them up, I go 1, 2, 3, and then I come back and start filling them in. So yeah, excellent. You remembered that. So although it doesn't really matter for this particular question, it will matter for determining whether things are magnetic or not. So let me fix that one. Got a little carried away. Okay, so now this is what my setup looks like. So now let's count the number of electrons in bonding versus anti-bonding orbitals. How many do we have in bonding orbitals?
4.
2, 3, 4, right. And how many in anti-bonding orbitals?
2.
2. Divide that by 2. What's my bond order?
1.
Mm-hmm. Now, that's relatively straightforward to think about. 1, that's a single bond. So B2, or, divalent boron, however you want to think about it, if that's possible. I can make a B2 molecule with a single bond. That's definitely theoretically possible. Now, is that more or less stable than B2 plus?
More stable because it's a complete bond.
Exactly. It's sharing a pair. So answering that question, the bond order for the stronger bond in each pair would be this one, and the bond order is 1. That would be the answer to that question. Do you want to do one more just to sort of nail this one down?
No.
Oh, go ahead. Yes.
Oh.
Yeah.
Sorry. I understand it now. Thank you.
All right, cool. Raymond, you had a question.
Do we need to copy it 7 times to write all the pairs?
No, I just put this here to sort of so you can put them in there. No, you just answer the question. Yeah, but you'll need this diagram in order to figure out where to put the electrons. So your job is to figure out how many valence electrons with each pair, how many valence electrons, where are they in terms of S and P, and then fill them in. And then just say, well, out of B2 and B2 plus, B2 has the stronger bond because its bond order is 1. That's it. And the same thing with B, C, and D. Yeah, you don't have to show filling this in every time. That takes up a lot of space. But like on a test, I would print this out as many times as you needed, because I wouldn't want you erasing it and putting in again. But for this exercise, yeah, you don't have to do that. All right, anybody else? Great question. Oh man, are we good on everything else? Or we can always come back to it on Thursday if you want to give these a try, and then we'll come back. We'll talk about them on Thursday, or any other question. So Thursday will be completely open. If there's like anything in any of the chapters that looks unfamiliar or was confusing the first time around, we can talk about it then, or talk about it now. But so does anybody else have any questions they want to review from this?
For like question 8, it says predict.
Question 8?
Yeah, it says predict the Vesper geometry. So does it mean we cannot draw it?
No, you should draw it. Yeah, I mean, I guess from that question, it doesn't say you have to draw it, but I mean, you probably should to give you an idea, because there's really no other way to figure out how the electrons are arranged unless you actually draw the structure. So I would definitely draw the structure.
Okay.
Yeah, because there's unless you can imagine these things in your head. Yeah, that's kind of hard to do.
Okay.
Would you like to do one, or should we do one of these, or?
No, just
No?
ask, shall we draw it?
Okay. All right, Ahmed, I'll see you later, man. So everyone's good. Everyone just wants to get at it, and we'll review on Thursday. Is that the way you'd like to proceed?
And
Okay. Not seeing anything on the chat. So if you don't have another question, I'm just going to have to say bye-bye.
Oh, I do have a question.
Raymond's got a question. Yes.
So for like resonance, for example, ozone, what's the electron configurations on oxygen 2, for example, on the
So it looks like that, right? So we have so if the central oxygen is positive and one of the peripheral oxygens is negative.
sp2.
sp2, right. One region there, 2, 3. So 3 regions of electron density. So sp2.
So how is the electron configuration look like sp2, 3 sp2 and 1p orbital? I mean, but is it like resonance form? But so I mean, it's the resonance is hybridized. I mean,
yes.
how we put the electrons in the boxes.
So 6 valence electrons. No, 5 valence electrons actually. So it would be 1, 2, 3, 4, 5. So this is your lone pair. This makes a sigma bond, this makes a sigma bond, and that one makes a pi. But it's 5 valence electrons.
Okay.
Yeah. But it actually doesn't ask you that in this particular question. It just asks you to predict the geometry. So basically, which general group does it fit in? And then the precise molecular shape. So the molecular shape includes lone pairs. That's the difference. You have to take into consideration lone pairs.
Okay, thank you.
Yeah, no problem.
Professor?
See.
For recitation 11, did you happen to figure out if nitrous dioxide?
Yes, I did. In fact, I looked it up just before we came. Great, you asked that. Yeah, so that was this, right? And isn't that the structure of it, I believe? It basically looks like CO2, but it has nitrogen in the middle. So instead of carbon would be neutral because it has those 4 valence electrons, nitrogen is positive because it usually has 5 valence electrons and only has 4. It turns out, well, anyway, what's your guess?
I would say it is polar, like pointing down.
Why would it be so there'd be a dipole pointing this direction?
Well, I'm sorry, because that's what I was thinking, but then I was looking at the plus as like
no, just ignore that. Just it would be think of it like this, because this is actually the way it's written. It's written like this.
So it would be linear. It would be nonpolar.
Right. It's nonpolar.
Okay.
Because we have a dipole because of the shape, and we have a dipole pointing in this direction. We have a dipole pointing in that direction, and they're exactly the same size, and they're pointing in exactly opposite directions, so they cancel each other out, and there is no net dipole. So it's one of those rare molecules that has a charge, but it's not polar. So it does happen. If all of the dipoles cancel each other out, it doesn't matter whether there's a charge or not. It's still not polar. Yeah. So I thought that was the case, but then I wasn't sure. But that is the case. So yeah, I'm glad you remember that, because I actually did, like, what, 5 minutes before I made sure I double checked that. And yeah, it's nonpolar.
Okay, and then so for the actual structure, I'm just confused. The nitrogen, isn't it supposed to have 5 valence electrons?
Right. That's why there's a net positive charge.
Oh, okay.
Mm-hmm. But basically, what happens in this situation is that we have there's like basically 4. There's electron density on both sides, and since nitrogen has a net positive charge, it pulls electron density away from the 2 oxygens and toward itself. Because even though nitrogen is not as electronegative as oxygen, it's really close. And nitrogen plus is more electronegative than oxygen. And so it pulls electron density toward itself. And basically, so it spreads, so the charge density is evenly spread throughout the whole molecule. And so it leads to it being nonpolar. You have basically the same electron density all the way around, but it's just 1 electron less than it would be otherwise. Yeah, there's a lot of interesting chemistry going on with NO2. It's pretty reactive, which is one of the reasons why it's considered like a noxious pollutant. You don't when you get your car smog, that's one of the things that's looked for. You measure NO and you measure NO2. They're both very reactive molecules, and you want to keep those as low as possible. All right. Love talking about chemistry. Anybody else before we wrap it up? Okay. So think about, go over this obviously, and look at the, go over the slides. If there's any of the stuff we did in class, and the problems we did in class that you don't remember, or previous recitation questions that you just didn't understand or didn't make a lot of sense, bring them on Thursday and we'll go through all of them, okay? Okay. Anyway, have a good, well, I would tell you to go have a good afternoon. This would be a good afternoon to read a book, curl up with, you know, your dog or your cat and then have a nap. It's that kind of afternoon. So do that if at all possible. So I'll see you on, I remember I have office hours tomorrow at 11, and then I'll see you in class on Thursday, okay?
Thank you, Professor.
All right, thank you. I'll talk to you soon.